Hello everyone, in this video we are going to learn about equilibrium points. Now by equilibrium points or equilibrium positions of any mathematical model, we mean points of zero rate of change. That means we are looking for those positions such that the derivatives which are governing that model are all equal to zero. Let's learn finding out equilibrium points through 5-6 illustrations in this video. Suppose there is a model which is given by, let's say, dx by dt equal to y and dy by dt equal to minus x. Suppose this is the coupled system given to us and we are expected to find out the equilibrium points of this system. Now for equilibrium, we just need to understand that equilibrium means those positions where the rate of change is zero. Now since there are two rates involved in this system, so for equilibrium we'll be looking for those ordered pairs x comma y such that dx by dt and dy by dt, both of them are zero at that particular point. So we are looking for those x comma y such that dx by dt has what value in this question? It has y equal to 0, that means, and the value for dy by dt is minus x, so that means minus x is 0. So that means we are looking for those ordered pairs x comma y such that what happens? Y is 0 and minus x is 0. So that means we are looking for those ordered pairs such that x is 0 and y equal to 0. So the only possibility that means is 0, 0. So that means 0, 0 is the only equilibrium position for the system that we started with in this example. Now let's do 2-3 more problems to understand the idea of finding equilibrium points and how to find them. Let's look at the second example now. Suppose there is a model which is given by dx by dt equal to, let's say, 3x minus 2xy and dy by dt is, say, xy minus y, and we are expected to find the equilibrium positions. Please note carefully that whenever you are finding equilibrium positions, you have to consider those positions for which the rates of change which are mentioned in the model, all the rates of change should be zero. So here, since there are two rates involved, so for equilibrium, we'll be considering those ordered pairs in this question such that dx by dt is 0 and dy by dt is 0. So let's see what are the possibilities that we have here. When we equate dx by dt, that means 3x minus 2xy. So what do we want here? We want 3x minus 2xy to be 0 and we also want xy minus y to be 0. We want both these to be true. So looking for those x comma y such that here you can see that 3x minus 2xy is 0. This has two possible, alternatives. Either x is 0 or, since x is common here, or y is equal to 3 by 2. These are the two options. Because x is common, you can write it as x into 3 minus 2y equal to 0. So when product of two expressions in real numbers is 0, then either this is 0 or this is 0. So this leads to two possibilities. Either x is 0 or y is 3 by 2. But we, together with this, we want this to be 0 as well. Now here y is common and you can see there are two possibilities. Either y is 0 or x is 1. So what do we want? We are looking for those ordered pairs x comma y such that this is 0 and this is 0. But this 0 has two options and this 0 again has two options. We want both these to be true. This should be true, that means this 3x minus 2xy should be 0 and xy minus y should be 0. Now 3x minus 2xy can be 0 if either x is 0 or y is 0. So let's move step by step. Let's freeze this option. Let's take x to be 0 and look for what all combinations we can have. If x is 0, this surely is 0. Dx by dt is surely 0. Let's see when can dy by dt be 0. When we club it with x equal to 0. So freezing x equal to 0, what are the possibilities for y? If x is 0, this dx by dt anyhow is 0. Let's see how can we make dy by dt as 0. Now how can dy by dt be 0 if either y is 0 or x is 1? So clubbing x equal to 0 with y equal to 0 leads to one option, 0, 0. Now clubbing x equal to 0 with x equal to 1 is inconsistent, because if x is 0, it cannot be equal to 1. That means this does not go with this. So freezing this and combining it with both the options for the second equation, we have only one possibility, which is 0, 0. So this is done. Now let's freeze the second option for the first equation. Here y is 3 by 2. Let's freeze this option now. Let us see what are the possibilities for x. If y is 3 by 2, then dx by dt is surely 0. Let us see what to combine y with, y equal to 3 by 2 with, so that this is also 0. We cannot combine y equal to 3 by 2 with y equal to 0, because if y is 3 by 2, it cannot be equal to 0. So that means we can only combine this with x equal to 1 to get the second equilibrium point, which is 1 comma 3 by 2. So that's how we move step by step, so that nothing is left out and all equilibrium points are covered in this process. The only simple thing that one needs to understand is that when you are looking for equilibrium points, you have to make sure that both the derivatives dx by dt and dy by dt should be together 0. If dx by dt equal to 0 has some options and dy by dt equal to 0 has some options, then you have to explore all the combinations, and the best way is to freeze one option for the first one and then look for all possible combinations that you can have for the second one, and then then you freeze the second option for the first one and then apply all combinations to land into all the equilibrium points. So let's do 2-3 more examples to understand this better. So these two are the equilibrium points of the given system, are the equilibrium points or equilibrium positions of the given system. So next example, let's see, dx by dt, let's say, is 2x minus xy, and dy by dt is y minus xy. Now for equilibrium, we want dx by dt to be 0 and dy by dt to be 0. So let's impose this equality to 0 as, the definition of equilibrium in itself says that the points which correspond to 0 rate of change. So for equilibrium, your rates dx by dt and dy by dt both should be 0. Now let's see what are the options. Since dx by dt equal to 0, that means 2x minus xy is 0. This is true, and y minus xy should be 0. Now how many possibilities are there for this expression to be 0? Since x is common, you can either have x to be 0 or y to be 2. And together with this, what do you want? Here y is common, so either y should be 0 or x should be 1. I can put a slash here. Since I put a slash here, so I prefer putting a slash here too. So this equation will be 0 if either this is true or this is true. This equation will be 0 if either this is true or this is true. Now we have to combine. We want those ordered pairs such that dx by dt is also 0 and dy by dt is also 0. That's the definition of equilibrium. This is what I am looking for. So let's see. If I freeze this option for dx by dt to be 0, I have to explore it with the first option for the second equation and second option for the second equation. If x is 0, one of the possibilities is y equal to 0. So the equilibrium positions happen to be 0, 0. When I combine, I have frozen this option, combining with the first option for the second equation. Now let me combine this with the second option for the second equation, but this is leading to some inconsistent solution, because if x is 0, x cannot be equal to 1. So that means this cannot be combined with this. So now let's freeze the second option for the first equation. So let's freeze 2 here. If y is 2, y cannot be 0. So that means this will not go together with this. So y equal to 2 can be combined only with x equal to 1 to give you the second equilibrium point, and these are the two equilibrium positions of the system that we are discussing. Let's do one more question to understand the idea better. Let's look at this one now. This is a special question. It will tell you a lot about equilibrium points. So far we have been getting a finite number of equilibrium points in the questions that we have discussed so far. Look at this one. This is an interesting question. Let's find out the equilibrium positions of this system now. Now again, I start with the same definition, because for equilibrium, what do we want? We want dx by dt to be 0 and dy by dt to be 0. Now dx by dt has this definition, so that means y minus 2xy is equal to 0, and we want xy minus y square should be 0. Now let's look at the possibilities for this to be 0. Here your y is common, so you have this as 0, and you also want this to be 0. So that means either y is 0 or x is 1 by 2. And from here you have two options, y equal to 0 or x equal to y. Now let's look for combinations. We are looking for ordered pairs x comma y such that this should be true and this should be true. Now if I combine y equal to 0, freeze y equal to 0 from the first option. Now the first option for the second equation also happens to be y equal to 0. This means that if I put y as 0, no matter what my x is, both dx by dt and dy by dt will be 0. You can look at the equations again. If I take y equal to 0, obviously dx by dt is 0, and here also if I put y as 0, then dy by dt is 0. So that means irrespective of the choice for the variable x, the first coordinate x, whatever that first coordinate may be, if my y is 0, this x comma 0 is going to become an equilibrium point. That means x can take any real value here. So this means this system of equations has an infinite number of equilibrium points because my x is free. So any point of the form x comma 0 is serving the purpose. Let's combine with other options now. X comma 0 type of point is surely an equilibrium point. Now let's combine y equal to 0 with this option. If you combine y equal to 0 with this option, x equal to y is 0 and x equal to y, that means x is also 0. So that's the second option that I am getting. Now let's freeze this and combine it with this. If x is half, y is 0. That's again a possibility, combining this with this. Now the last part is combine this with the last part here. So 1 by 2, and then x is 1 by 2 and x is equal to y. So that means 1 by 2 is also an option. Now observe carefully that this point 0, 0 is already included in the points of the form x comma 0. This point half comma 0 is also included in the same category because it also looks like x comma 0 for x equal to half. So that means this is the only point which is not included in this category. So in a sense, you can say that equilibrium points here for this system are infinite, and equilibrium points are the following. Number 1, half comma half, and number 2, any point of the form x comma 0 happens to be an equilibrium point. So this system has an infinite number of options for equilibrium positions. So mind it, when you have two options, see, let's say you have first equation, okay, eqn 1, dx by dt to be 0, eqn 2, dy by dt to be 0. Suppose this has two options, let's say a and b. This has two options, let's say c and d. You want both the equations to be 0, both the equations to be satisfied, right? So what will you do? You will freeze a and try a with c, try a with d, and look for the possible consistent solutions. Next, you freeze b and try b with c, try b with d, and that's how you cover all possible equilibrium points and you do not miss out any. So that's how you find equilibrium positions. Let's go to one system of equations which is involving, let's say, more than two equations. Let's consider the system. Let's a system which has three variables, let's say x, y, z. Suppose this is the system which is given to you, ax minus b, let's say a1x minus b1xy minus c1xz. That's the model for the predator-prey interaction, which we'll be discussing in subsequent videos. But let's now, right now we are just focusing on finding out the equilibrium positions. So let's look at this question as a question of three equations, three dependent variables. Suppose this is the system and we are expected to find out the equilibrium points. Now first of all, be cautious. In the earlier equations, there were two variables x and y appearing. So your ordered pairs of the form x comma y, where dx by dt equal to 0 and dy by dt equal to 0 were corresponding to your equilibrium positions. Here it's a system which is involving three equations. So your equilibrium position this time is not going to be an ordered pair. It's going to look like a triplet x comma y comma z. such that dx by dt is 0 and dy by dt is 0 and dz by dt is 0. So you want all three rates to be 0. That's what an equilibrium position is going to mean in this. Now let's see what is dx by dt equal to 0 meaning. In this system, it's a1x minus b1xy minus c1xz, and we can see that x is common in all three terms. So by dx by dt equal to 0, we would mean that either x is 0 or you can see a1 minus b1y minus c1z is 0. That's the option that you have for dx by dt equal to 0. You want and dy by dt equal to 0, right? Let's see what is dy by dt. Here again, luckily y is common. So you have two possibilities here for dy by dt to be 0. Either y is 0, you can see either y is 0 or x is b2 by a2, right? Because a2x minus b2 equal to 0 means x is b2 by a2. So this has two possibilities. Again, let's look at dz by dt equal to 0. Z is common here. So this means either z is 0 or x is b3 by a3. Now the challenge here would be to take those triplets such that all three are together 0. Now how do we go about such questions? Again, in a similar fashion, you take one option, freeze one option for dx by dt equal to 0. That's 0. Okay, so my x is 0. Let me see what all can I combine it with, so that I get dx by dt is 0 and dy by dt is 0 and dz by dt is equal to 0. If I combine x equal to 0 with this first option for dy by dt, I get 0. Obviously, I cannot combine x equal to 0 with x equal to b2 by a2, because if x is 0, it cannot be b2 by a2. So this combination is inconsistent. This will not go with this. So this can only be combined with dy y equal to 0, and that leads to dy by dt equal to 0. Again, x equal to 0 can be combined with this or this, but if x is 0, x cannot be b3 by a3. So that means this cannot go with x equal to 0. So the only option left is z equal to 0. So 0, 0, 0 happens to be one equilibrium position. So when I froze x as 0, the only possibility which I got from the other two equations was y equal to 0, z equal to 0. Right? Now let's freeze the other option. What is the other option? Let's freeze something else to be 0. Suppose I freeze y to be 0. Let's combine y to be 0 with something else. If y is 0, I've already combined it with x equal to 0. So I'm not looking here for this option. If y equal to 0, I can combine it here with this. See, I am freezing y equal to 0 now and exploring the other possibilities for the other equations. If y is 0, I cannot combine it with x equal to 0 because I've already done that here in the first point. So let's not repeat that. If y is 0 and I put it here, y is 0 means z is a1 by c1. Put y equal to 0 here, you get z is a1 by c1. So that means I've combined this with this. Now since one equation here is satisfied, one equation here is satisfied, so I do have dx by dt equal to 0 and dy by dt equal to 0. When can I have dz by dt equal to 0 now? Now since I cannot combine it with z equal to 0 because z is already frozen, so I can only combine it with x equal to b3 by a3 to get the other equilibrium position. So I hope it's clear to everybody that I am just freezing the first option for the first equation, then I am freezing the first option for the second equation. Now I am going to freeze the first option for the third equation and explore all possible combinations. If z is 0, this is already satisfied, dz by dt equal to 0. So let's combine it with the other possibilities. If z is 0, x equal to 0, y equal to 0 has already been covered. So let's not look at that. Z equal to 0 combined with this equation gives you y equal to a1 by b1. So that freezes my option for y. Z equal to 0 combined with this is already done. Z equal to 0 combined with this freezes the option as y equal to a1 by b1. Now let's see what is the option for x then. Now since y is already frozen, y cannot be 0. If I freeze z equal to 0, dz by dt is already made as 0. If I am putting my y as a1 by b1, this is also satisfied. So the only equation left to be satisfied is this. Now when can dy by dt be 0? Y equal to 0 or x equal to b2 by a2. But y equal to 0 cannot be the case because y is already frozen. So now the only possibility is that this has to be b2 by a2, and that's what gives you all possible combinations you have explored, because first you froze the first option for the first equation and then explored all the possibilities. Then you froze the second option for the second equation and explored all the possibilities, and then you froze the third option for the third equation. You froze the first option for the third equation and you explored all the possibilities. So these are the equilibrium points. There are 3 equilibrium positions for this system and they are given by this. So these are the equilibrium points. So I hope finding equilibrium points is a very logical technique. You just have to, the definition says you have to look for those points which correspond to zero rate of change. Now zero rate of change means zero rate of change for all the variables together. So there's an and in between. You want dx by dt equal to 0 and dy by dt equal to 0. Now whenever dx by dt equal to 0 has more than one option and dy by dt equal to 0 also has more than one option, and if there's a third variable, let's say dz by dt, that also has more than one option, then the best way to deal with it is you freeze the first option for the first variable and then explore all combinations for the second and the third equation. Then freeze the first option for the second variable and explore options, all the other options, and then freeze the first option for the third equation and then explore, so that you do not miss out on any of the equilibrium points. So this was all about equilibrium positions. In the next video we are going to do some phase plane analysis of some nice mathematical models. Till then, thanks for watching. Stay tuned.